Hello, everyone. It is now time to compute the inverse of 3 by 3 matrices. Actually, I'm so amazing that the technique I'm going to show you to compute the inverse of a 3 by 3 will work for any square matrices n by n. But in this class, we only need for our applications to compute inverses of 3 by 3. And the really good news is that technically speaking, the way we're going to be computing the inverse of a 3 by 3 or in general n by n is by using the Gauss-Jordan elimination algorithm. So it's not a new computation. There's a little bit of a setup, but once you set up your question correctly, the computations are really simply I'm quoting here, an application of the Gauss-Jordan elimination algorithm. So what's the idea here? So it starts with a nice little set of facts that I summarize in a theorem. So when there is an inverse, we've already saw together for 2 by 2 that this is only possible when the determinant is not 0. This is still true for 3 by 3, and it would still be true for n by n. Of course, we did not cover how to compute determinants for n by n in general, but we know how to compute determinants for a 3 by 3. So if you have a 3 by 3 matrix and you're asked to compute the inverse, if you compute the determinant and it's 0, there's no inverse. If it is something different than 0, then there is an inverse. How do you compute it? Well, here we're going to use this very powerful third point here in this theorem that when the inverse of a matrix exists, when the determinant is not 0, that matrix A, if you apply the Gauss-Jordan elimination algorithm in its full glory, so until it's in a whole reduced echelon form, actually the matrix A is equivalent, is similar to the identity matrix IN. So if your A is invertible and you do Gauss-Jordan in its full form until you get something in a whole reduced echelon form, it will be the identity matrix. So how can we use this? And here the method to find the inverse of an n by n. So this works for any square matrix. Again, we will only practice this on 3 by 3. The first step is to construct what we call the super augmented matrix, where you have the matrix A on the left side and you super augment that matrix with the identity matrix. So for us, most of the time, we're simply going to be using, since we have a formula for 2 by 2s, we don't care about 1 by 1. So for us in particular, so just as a small remark here, we're going to augment our 3 by 3 matrix with the identity matrix I3. And then once you have this super augmented matrix, you apply the Gauss-Jordan elimination algorithm on it. And then what will happen when A is invertible, so when the determinant is not 0, when you apply Gauss-Jordan, the row reduced echelon form of the super augmented matrix will always be such that on the left side, you will get the identity matrix as predicted by the third point of this theorem. And then on the right side, where you used to have the identity matrix, that brand new matrix, after you do your Gauss-Jordan elimination algorithm, after you do your swapping, your elimination, your rescaling, what you're going to have left on the right side will be what you're looking for, the inverse of that matrix. So in other words, if you take your matrix A, you want to compute the inverse, you construct the super augmented matrix A augmented by IN, you apply Gauss-Jordan until you get IN augmented by some shit, and that shit, my friend, is what you're looking for. This works for every size, but we're only going to do it for 3 by 3 in this class. If you forget to compute the determinant in order to decide if the matrix is invertible or not, what will happen if you start right away, if you construct your super augmented matrix and you apply Gauss-Jordan? Well, what will happen is this nice little remark, and we'll do an example like this where we're going to fake that we don't know that there's no inverse. And then if you apply Gauss-Jordan, what will happen is that you're going to get at some point during your algorithm a row of zeros in the left side. So if on the left side of the super augmented matrix, you get a row of 0. This means that there's no inverse. This means that the determinant is 0. You can just stop there. There's no inverse. And actually, our first example will be exactly like that. So my first example. So here, let's do our first example. I only have 2 examples because this computation will happen a lot in various sections. So let's find the inverse of the matrix A: 1, 2, 0, 3, minus 1, 2, minus 2, 3, and minus 2. So let's try to compute the inverse. So just as a remark, and this is a very fun exercise, if you do compute the inverse of this 3 by 3, and please do so, this is a very nice exercise, you will see that the determinant is 0. And on a test, if I'm asking you to compute the inverse of a matrix and you compute that the determinant is 0, you just say that there's no inverse and you stop there. You don't do anything. But suppose we're a lazy piece of shits, okay, and we say, nah, I'm not computing the determinant. Let's just try it. Let's just apply Gauss-Jordan, and let's try to milk out a possible inverse. So the setup, very, very crucial. So the first thing you do, and there's marks for that, just construct your super augmented matrix. So on the left side, you have your matrix A: 1, 2, 0, 3, minus 1, 2, minus 2, 3, minus 2. And then on the right side, you have I3. Remember, I3 is the square matrix where you have 1 along the diagonal, and everywhere else you have 0s. So just to be clear, okay, because you're going to get marks just for that part. So we have A here, and we have I3. And this is the inverse question, okay, for test or final exam. So let's go. So we do Gauss-Jordan. We don't really care. We have a 3 by 6. It does not matter anymore. Where is this super augmented matrix come from? You apply Gauss-Jordan. So here I'm lucky on my first row. I have a 1. I start my elimination to destroy the 3 and the minus 2 under. So to destroy the 3 on row 2, I'm going to say that row 2 is row 2 minus 3 times row 1. And to destroy the minus 2, I'm going to say row 3 is row 3 plus 2 times row 1. So I'm using my future pivot, the 1 as the eliminator. So again here, when I'm doing Gauss-Jordan, very quickly but carefully, I can rewrite the first row without changing anything. Of course, I'm going to get a 0 here and here. That was the point of choosing those 2 eliminations. But then I need to carry on this operation throughout. So minus 1 plus 3 times 2. Minus 1 minus 3 times 2. That will give you a nice minus 7. 2 minus 3 times 0, that's 2. 0 minus 3 times 1, that's minus 3. 1 minus 3 times 0, that's 1. 0 minus 3 times 0, that's 0. And again, for the next row, so if you go 3 plus 2 times 2, that's 7. Minus 2 plus 2 times 0, that's minus 2. 0 plus 2 times 1, that's 2. 0 plus 2 times 0, that's 0. And 1 plus 2 times 0, that's 1. All right, so now I continue. So again, here I'm done with my first row. I'm going to find the next column from the left with non-zero entries. Of course, I see the second column here is what I want. And of course, I see on the left side that this minus 7 can easily be destroyed. So I'm going to keep that minus 7 for now as an eliminator. I'm going to kill the 7 under it by simply saying that my row 3 is going to become row 3 plus row 2. And this will cancel that. So again here, not changing row 1, not changing row 2. I can rewrite these 2 rows quickly but carefully. So when I go 0 plus 0, that's 0. 7 plus minus 7, that's 0. That was the point of doing that elimination. Minus 2 plus 2. We're so good at elimination that we're destroying a lot. So 2 plus minus 3, that's minus 1. 0 plus 1, that's 1. And 1 plus 0, that's 1. So again, I failed to mention this, but that bar in the middle is just to remember that we constructed that specific matrix using A super augmented by I3. But when I'm doing my row operations, I have 3 rows with 6 entries. So make sure you do the operation on the full row. But anyways, so here, what happens is that you can see in this question that on the left side, I get a row of 0. You can stop. If I'm looking at the positions of my pivots, I will have one here, and the next one will be on the augmented part. That when that happens, automatically, you can see that A has no inverse. Okay, so that matrix has no inverse, and you can stop. Okay, this again could have been caught from the beginning by computing the determinant of that matrix. But normally, we're going to ask you to compute the inverse when there is actually an inverse to compute. So let's do an example where the inverse does indeed exist using this method. And again, what's truly powerful with this method is that this is not supposed to be a new computation. If you're comfortable with the Gauss-Jordan elimination algorithm in its full glory, when I say in its full glory, until you get something in a hoch-reduce echelon form, then you're good to go. Okay, so next example, let's find the inverse of 270, 1, 4, minus 1, and 1, 3, 0. I will call that matrix A. So I'm constructing first my super augmented matrix, A augmented by I3. So I write A, so that 2, 7, 0, 1, 4, minus 1, 1, 3, 0, super augmented by the identity matrix, so a matrix filled with zeros, except on the diagonals, where I have 1. So my first pivot could be on the first row, but here I'm going to use one of my favorite trick where if I choose 2, at some point I'll have to divide by 2, and this row has a 7. This would create fraction. If you see a 1 or a minus 1 below the pivot you're trying to construct, like here, I'm really tempted. Let's take this 1 up. So here I'm going to use a step that is not really Gauss-Jordan, but this is a very, remember this is a very powerful trick. If you see a 1 or a minus 1, it's time to swap. Okay, so this will really simplify your computation. So I have my star move here. Okay, so my little star move. So if you swap row 1 and row 2, I could have chosen row 3, of course. It really does not matter. But here I decided to swap row 2. I have now my first row. So very quickly here, as usual, not changing row 3. My row 2 is now row 1. So just be careful when you're rewriting it. And my row 1 is now row 2. And make sure you do it on the 6 elements of the rows. Okay, so there's 3 rows with 6 elements. So you have to swap everything, even the stuff in the augmented part. All right, let's go. It's time to eliminate some stuff here. So I have my 1. I want to destroy shit on the, so the 2 and the 1. So I'm going to say, for example, I can say row 2 is going to become row 2 minus 2 times row 1. And row 3, to destroy that 1, I'm just going to go row 3 minus row 1. So again, very quickly, but carefully, not changing my first row. Of course, I'm going to get zeros for those 2. That was the point of that elimination. And now when I do my operation, 7 minus 2 times 4, that's minus 1. 0 minus 2 times minus 1 is going to be plus 2. 1 minus 2 times 0 is 1. 0 minus 2 times 1 is minus 2. And 0 minus 2 times 0 is 0. And then again for the third row, of course, 1 minus 1 is 0. 3 minus 4 is minus 1. 0 minus 1 is plus 1. 0 minus 0 is 0. 0 minus 1 is minus 1. And 1 minus 0 is 1. All right, now I just continue. So this is good practice for Gauss-Jordan at the same time. So my next pivot here is going to be on the second column. It's already a minus 1. I'm okay with minus 1. So here you have a choice. You could rescale and destroy. I decided to destroy first. It really does not matter as long as you do it correctly. So boom, I'm going to destroy. So by saying row 3 is going to become row 3 minus, remember you have to use row 2, minus row 2. So again here, very quickly but carefully, I'm not touching the first or the second row. So I rewrite those 2 quickly but carefully. Of course, 0 minus 0 is 0. Minus 1 minus minus 1 is 0, 0. That was the point of that elimination. But now 1 minus 2, that's minus 1. 0 minus 1, that's minus 1. Minus 1 minus minus 2, that's going to be plus 1. And 1 minus 0 is 1. And now I already know that this is going to work because I see where my pivots are and they're not going to move. My pivots are on the diagonal. I know the whole reduced echelon form will have the identity matrix on the left side. I just need to continue. And here it's not a choice. You really need to persist until you get the identity on the left side. So let's go. So here I'm going to rescale my row tree. I want all my pivots. I could have done both of them at the same time. Actually, I would have done that. But since the things are already there for me, where I'm just missing the operations, the only thing that we did at that step is rescale row 3. So we said row 3 will be turned into minus 1 row 3. So I'm just multiplying by minus 1 throughout. So again, not touching row 1, not touching row 2. And I'm multiplying by minus 1 everywhere, so quickly but carefully, and I get my computation for my last row. And now that I have a 1, I want this one to be alone in its column, so I'm going to do 2 elimination to destroy the 2 and the minus 1. So again, very good exercise to practice Gauss Jordan right here. So I'm going to say row 1, the way I'm going to destroy that minus 1 is by saying row 1 plus row 3, and row 2 will become row 2 minus 2 times row 3. Remember, I'm using my third row as the eliminator. So again, I'm not touching row 1. Again, of course, I'm going to get zeros there. That was the point of that those two elimination. But I have to carry out my operation throughout. And again, the power of when you do Gauss Jordan, hopefully you're getting a bit better at it. But because I have 2 zeros, I know that these numbers are not going to change in the first 2 columns. So I just need to carry out the operation in the augmented part. So let's do row 1 first. 0 plus 1 is 1. 1 plus minus 1 is 0. And 0 plus minus 1 is minus 1. And now for row 2, 1 minus 2 times 1, that's minus 1. Minus 2 times minus 1 will be plus 2, which will give me a 0. And 0 minus 2 times minus 1, that's plus 2. Now my rightmost pivot is 1. It's also alone in its column. So now I move to my next pivot. So here my next pivot is minus 1. So I'm going to rescale it. I could have done this earlier, but this is the order I chose for now. So row 2, let's rescale it simply by multiplying it by minus 1. So not too difficult of an operation. So not touching row 1, not touching row 3. And I'm multiplying everywhere by minus 1. So I'm just changing the sign quickly but carefully. And now all my pivots are 1. My first and my last one are alone. I just need one more elimination. So let's go row 1. Let's get rid of that 4 with row 2. So row 1 will be row 1 minus 4 times row 2. And now here we go. So you can see here, I'm not touching row 2. I'm not touching row 3. Of course, 1 minus 4 times 0 will be 1 again. 4 minus 4 times 1. Of course, you're getting a 0 here. That was the point. Those two zeros playing with each other will not do anything. 1 minus 4 times 1, that's minus 3. 0 minus 4 times 0, that's 0. And minus 1 minus 4 times minus 2, which is plus 8, will give you 7. And now, and this is very crucial, you stop. I mean, this matrix is in the whole reduced echelon form. All the pivots are 1. They're all alone in their respective column. And when I look at my final matrix in a whole reduced echelon form, so this is in a whole reduced echelon form, that part here will always be the identity I3. And that part here, my friends, the leftover is going to be what I'm looking for, the inverse. So A inverse is minus 3, 0, 7, 1, 0, 1, 0, minus 2, and 1, minus 1, minus 1. And here, if you want to check if your answer is right, I will never force you to do that. But if you want to feel it, and this is good when you're learning that stuff, this is good for also practice, to also practice matrix multiplication. But if you multiply A by this brand new matrix, or if you multiply this brand new matrix by A, so here my original was in blue and this one is in red, do the multiplication and verify in both cases. If you do A inverse times A or A times A inverse, what you're going to get is the identity matrix I3. So this is good practice for matrix multiplication also. Okay, so I'll let you do that on your own. But this is something that will guarantee that your computations are right. So, and it's good practice. You're still probably learning how to multiply two matrices. So when you're trying to learn to master Gauss-Jordan, the Gauss-Jordan elimination algorithm, and you're trying to master matrix multiplication, this is a perfect example. Master Gauss-Jordan to get that inverse and master matrix multiplication by checking if your answer is such that when you multiply A by that answer or that answer times A, you get the identity matrix. Anyway, so much passion for not much. But like I said, to some extent, there's no new computations to compute the inverse. There's just a little bit of setup. So you want to compute the inverse of A, super augment that matrix with the identity matrix. For you guys, it's going to be I3. Put this matrix in row reduced echelon form. Your matrix in row reduced echelon form will be, when A is invertible, will be I3 augmented by some shit. And that shit is what you're looking for. That's the inverse you're looking for. Anyways, for this nice little section that reviews Gauss-Jordan to compute the inverse, where you can double check your stuff with matrix multiplication. That's it. That's all. Bye-bye.